Most of us imagine the limit of human space travel as a speed problem. Build a faster engine, carry more fuel, and the frontier slides outward. First the Moon, then Mars, then the outer planets. Given enough time, perhaps we could follow our interstellar probes into the dark. But distance may be the least troublesome part. A spacecraft leaving Earth doesn't simply move across a larger map. It begins losing the systems that make human life on Earth seem almost effortless. A rescue takes longer. A doctor can advise the crew, but can't place a hand on the patient. A replacement part may be months away, assuming anyone can send it at all. Even a simple conversation starts to stretch, until asking Earth for help feels less like making a call and more like exchanging letters. And humans are wonderfully dependent creatures. We rely on farms we never see, technicians we never meet, factories making tiny parts we don't know exist, and hospitals stocked by supply chains crossing whole continents. Put a few people inside a spacecraft, and all that hidden support has to follow them somehow. Earth does not go with you. That changes the question. The frontier isn't just the farthest place a rocket can reach. It may be the point where the crew can no longer count on rescue, repair, fresh supplies, or timely advice from home. The engines might still be working perfectly when that line is crossed. Tonight, we're going to find where that line begins to appear, and why it may sit much closer to Earth than our maps suggest. If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. The Moon looks close on a map. Apollo crews crossed the gap in about 3 days, which sounds less like an expedition and more like a long weekend with unusually complicated luggage. That travel time does something misleading to your instincts. If a place is only a few days away, you expect Earth to remain within reach. A broken part can be replaced. An injured person can be brought home. Someone can send whatever you forgot to pack. 3 days feels short enough for help to remain ordinary. That's how rescue works around us. A hospital doesn't manufacture its own medicine. A town doesn't need to grow every meal within its borders. When something local fails, roads, power lines, warehouses, repair crews, and nearby cities quietly fill the gap. Most of the time, we barely notice that support exists. Earth is full of invisible backup systems. On the Moon, those substitutions begin to disappear. Look up from the surface, and Earth is still there, bright and familiar. But the scene around you is black sky, bare ground, and no air at all. There's no weather, yet temperatures can swing between punishing heat and deep cold. Dust doesn't settle after rain because rain never comes. It clings, scratches, works into joints, and follows people back into whatever shelter they have. A small failure can therefore stop being small. A damaged seal isn't an inconvenience when the air is on the other side of it. A weak battery isn't just annoying when warmth, communication, and life support depend on stored power. A missing tool can't be replaced by driving to the next town. There is no next town, no local warehouse, and no repair crew coming over after breakfast. This is why NASA is drawn to the lunar South Pole and wary of it at the same time. Some areas may hold water ice in places sunlight barely reaches. Nearby high ground may receive useful stretches of light for solar power. Those features could help people produce water, oxygen, and fuel locally, instead of carrying every kilogram from Earth. But the same landscape is severe. Deep shadows make navigation difficult. Low sun throws long, confusing shapes across rough ground. Cold can settle into places that have remained dark for immense spans of time. The resources are valuable partly because reaching and using them forces every weak system into view. That makes the Moon useful in a way a comfortable place never could. It tests whether a crew can maintain air, power, heat, tools, spare parts, food, and communications, when Earth can advise but cannot simply step in. It exposes the awkward difference between bringing a machine somewhere and keeping people alive beside it. None of this means the Moon cannot be inhabited. It means habitation there has to be built around independence from the beginning. Every system needs to survive long enough for repair, and repair needs tools, parts, power, and people who can work while wearing gloves inside a suit that is keeping them alive. The Moon is close enough for Earth to fill the sky, close enough for radio conversations and missions measured in days. Yet, once you're standing on that airless ground, the ordinary meaning of nearby has already failed. Our nearest world is also the first place where home can be plainly visible and still unable to rescue you. Imagine a ridge near the Moon's south pole. Sunlight catches one side, while the floor of a nearby crater stays in permanent shadow. The two places may be separated by a short drive. They might as well belong to different worlds. Inside some of those shadows, temperatures can fall near minus 334 degrees Fahrenheit, minus 203 Celsius. Nearby ground in sunlight can reach about 130 degrees Fahrenheit or 54 Celsius. That's a swing of more than 460 Fahrenheit degrees, roughly 257 Celsius degrees, across terrain that may look almost identical from a distance. A house on Earth gets to borrow a remarkably gentle environment. The air spreads heat around. Weather moves slowly enough to predict. Dust usually stays outside when you close the door. On the Moon, those quiet favors disappear together. A rover parked in sunlight has to shed heat. Move it into shadow, and the same rover has to protect batteries, cables, lubricants, and electronics from deep cold. A route that looks simple on a map becomes a moving thermal problem. So does the time of day. So does where you park. And these problems overlap. Dust coating a radiator can make cooling harder in sunlight. Cold can stiffen a dusty joint in shadow. The machine doesn't get to face each problem separately, with a patient engineer standing nearby and a warm workshop waiting behind them. Then there's the dust. Lunar dust isn't soft garden soil. With no wind or water to smooth it, the grains remain sharp and cling to surfaces. They work into suit joints, electrical connections, seals, radiators, and moving parts. A door can close perfectly 100 times, then meet one dirty seal on the 101st. That sounds almost comically small. A hinge, a heater, a strip of rubber that no longer sits quite flat. Yet far from Earth, small failures stop being small. A contaminated joint can slow an astronaut. A sluggish mechanism can turn a routine repair into extra time outside. Extra time uses oxygen, cooling water, battery power, and the attention of everyone waiting inside. This is why NASA's moon base architecture treats the Moon as more than a destination. It's a place to reduce risk before sending people toward Mars. Crews can learn how to operate with less help from Earth, manage supplies, tolerate dust, maintain equipment, and make decisions when the neat plan has already gone wrong. The useful part is that the Moon is still close enough for support. Engineers can watch what fails. Replacement parts can arrive on a later mission. A crew can discover that a filter clogs too quickly. A glove makes a repair awkward, or a maintenance schedule only works when nothing unexpected happens. Mars will offer fewer second chances, so finding those weaknesses on the Moon is the point. That doesn't make a lunar base impossible. It makes the word base slightly misleading. This isn't a small Earth neighborhood waiting for a larger budget. For now, it's closer to a test range where every Earth substitute has to prove itself under cold, heat, dust, delay, fatigue, and limited supplies. And that may be the Moon's most valuable gift. It lets us discover, while rescue is still imaginable, which parts of living away from Earth we don't yet know how to do. So what would a crew actually need to survive long enough for those lessons to become routine? When we hear the word rescue, most of us imagine a spacecraft turning around. A warning light comes on, the crew stays calm, and someone finds enough fuel to bring everyone home. But turning around is only one small part of rescue. Think about what happens when someone gets badly hurt in an ordinary town. An ambulance arrives. A hospital has surgeons, medicine, blood, machines, and spare equipment. Specialists examine scans and tell the local team what to do. If one hospital can't handle the problem, the patient can be moved to another. You rarely notice this network until something goes wrong. None of it looks heroic by itself. It's a collection of services already waiting nearby. NASA treats distance from Earth as one of the 5 main hazards of human spaceflight because distance weakens that entire collection at once. Instructions take longer to arrive, replacement parts take longer, food, medicine, and other supplies can't simply be sent up tomorrow morning. Medical advice may still cross space, but the doctor can't step into the room. And evacuation, if it's possible at all, has to obey launch windows, spacecraft limits, and orbital mechanics. Rescue is less like one brilliant maneuver and more like keeping a remote town alive while its ambulance, hospital, warehouse, and phone service all fade together. Lose one service and the others carry more weight. Lose several and a manageable accident can become a mission-ending emergency. That's why the Moon and Mars belong to different operational categories before we compare their dust, gravity, or weather. A crew near the Moon is far away by everyday standards, but Earth can still act like a nearby emergency system. Communication is quick enough for a real exchange. Cargo and replacement vehicles can be planned on human timescales. A damaged crew may have a path home that takes days rather than many months. Mars removes that closeness. Depending on where the planets are in their orbits, a message can take minutes to travel one way. A reply takes minutes more. That sounds manageable until someone is bleeding, a machine is overheating, or an alarm has 3 possible causes. The crew can ask Earth for help, but they may need to act before the answer arrives. Earth can offer instructions. It can't hold the wrench, stop the leak, or steady the patient. Sending physical help is harder still. You can't keep a rescue spacecraft parked just outside Mars, stocked for every failure. Vehicles, crews, fuel, landing systems, and return opportunities all have to exist beforehand. Even then, the geometry between Earth and Mars decides when a trip is practical. The nearest spare part may be millions of miles away, and it does no good sitting in a warehouse in Florida. There isn't one clean distance where rescue suddenly becomes impossible. Different spacecraft, medical systems, supply caches, and mission plans move that boundary. A prepared crew might survive a failure that would end a more fragile mission much closer to home. But the direction is clear. As distance grows, Earth stops behaving like an emergency service and starts behaving like a distant advisor. The crew must carry more of the hospital, the workshop, the warehouse, and the escape plan with them. That is where a frontier begins, not at a particular mile marker, but where help from home is no longer nearby enough to count on. You can imagine the change as a short ladder. The space station sits on the first rung. The Moon sits higher. Mars is much higher still. At each rung, the crew carries more responsibility, while the practical reach of Earth grows weaker. From the International Space Station, a sick or injured astronaut can return to Earth relatively quickly. Supplies also arrive on a regular schedule. That doesn't make an emergency simple. It means the crew still lives inside a system that reaches all the way down to hospitals, laboratories, launch teams, and stocked warehouses on the ground. The Moon stretches that system. NASA often contrasts the trip in plain numbers. A trip to the Moon takes roughly 3 days. A Mars mission could keep a crew away from Earth for roughly 3 years. 3 days and 3 years sound like different versions of the same inconvenience. They aren't. A delay of days can sometimes be covered with spare equipment, extra medicine, or a carefully planned evacuation. A mission lasting years changes what must be planned for before the crew ever leaves Earth. Think about packing for a weekend away, then packing for several years in a place with no shops. You don't just bring more socks. You start making choices about every unlikely problem that might happen while you're gone. Which tools deserve space? Which medicines will remain usable? Which spare part is more important than another spare part? At some point, adding one protection means leaving a different protection behind. The awkward part is that you must choose before you know which emergency will arrive. NASA's medical risk work draws the same line more formally. Crews traveling beyond low Earth orbit may have limited or no resupply. Evacuation may also be severely restricted. At Mars, an injured astronaut cannot simply be placed in a capsule and delivered to a hospital that evening, or even that week. That changes medicine before anyone gets sick. The crew must diagnose more conditions themselves. They must treat them with whatever is already aboard. Doctors on Earth can still offer knowledge, but even conversation becomes slower. Depending on where the planets are, a message between Earth and Mars can take several minutes each way. No one on the ground can guide a delicate procedure as if they were speaking across a table. And some emergencies won't wait politely while everyone exchanges messages. This is the quiet point where old assumptions fall away. Earth may still track the spacecraft. It may still send instructions, calculate options, and help the crew make the least dangerous choice. But it can no longer promise to send the missing drug, replace the failed machine, or bring an injured person home before the injury decides the outcome. Mars isn't automatically beyond rescue in every sense. Mission designs can include spare systems, medical training, protected shelters, and ways to turn back during certain parts of the trip. Better spacecraft may shift the boundary again. The limit depends on the emergency and on what the crew brought with them. But Mars changes the meaning of backup. An emergency there is folded into local inventory, local judgment, and local endurance. The crew may hear Earth's voice clearly and still be unable to receive Earth's hands. So when rescue has faded into advice from far away, what does coming home mean then? Mars still looks like an expedition in most of our heads. A spacecraft leaves Earth, crosses a larger gap, lands, does the work, and then comes home. Apollo, only farther, more food, more fuel, more things that can break, but the same familiar shape. The distance begins to loosen that idea. NASA puts Mars about 140 million miles from Earth on average. That's about 225 million kilometers. The word average is important here. Earth and Mars keep moving around the Sun, so the gap between them changes enormously. You can't treat 140 million miles as a fixed road with Mars parked neatly at the end. And the spacecraft can't simply leave whenever everyone feels ready. Useful departure windows come from the positions of both planets. The crew has to travel when the moving geometry allows it, wait while Mars and Earth continue around the Sun, then return when the geometry works again. The planets set the timetable. Human impatience doesn't get a vote. That turns a mission into something much larger than a long flight. NASA describes a crewed Mars mission as roughly 3 years away from Earth. 3 years. Think about where you were 3 years ago, and how much ordinary life has happened since. Birthdays, illnesses, changed jobs, moved homes, friendships that grew or quietly disappeared. Now place that whole stretch of lived time inside one mission. Apollo crews measured their trips in days. A Mars crew would measure theirs in seasons and years. They would watch Earth's calendar keep moving while every meal, repair, medical worry, and disagreement happened inside the same small chain of machines. The voyage wouldn't interrupt life for a while. It would become life for a while. That changes how return risk has to be handled. On a short trip, coming home can feel like the natural second half of the plan. Go out, finish the task, turn around. At Mars scale, the return is another major operation waiting months or years ahead. Its hardware, fuel, supplies, and timing all have to survive everything that happens before the crew is ready to use them. You know the small version of this problem if you've ever packed for a week somewhere remote. Anything forgotten at home stays forgotten. Now stretch the week into 3 years, replace the suitcase with a spacecraft, and make the trip home depend on equipment carried through radiation, dust, temperature swings, and constant use. Earth can advise, it can calculate, it can send new instructions, but the mission can't outsource its physical return to a warehouse back home. So the real break from Apollo isn't that Mars adds more danger to the same adventure. Distance and duration change the kind of commitment being made. Before launch, planners have to place as much of the future as possible inside the vehicle. Spare parts, repair options, medical capacity, margins of food and power, and several ways for a bad day to remain survivable. Imagine the mission as a bar drawn across a calendar. It doesn't occupy a holiday or a season or even 1 year. It runs across several winters and summers, past anniversaries and changing faces at home. Near the far end of that bar sits the return trip, still waiting to begin. The ticket home is no longer the folded half of an expedition. It is another campaign, carried silently through an entire era of the crew's lives. It's tempting to imagine Earth still running the mission from a control room. The crew reports a problem. Specialists gather around their screens, study the data, and talk the astronauts through the fix. You can imagine the calm voices coming through a headset, almost as if the doctors were in the next room. Mars changes the conversation itself. Imagine a message leaving the surface. It crosses the thin Martian sky, then spends minutes traveling through black space. Depending on where the planets are in their orbits, a signal can take roughly 20 minutes to reach Earth one way, sometimes a little more. The answer needs about the same travel time back, so a simple exchange may take 40 minutes before the crew hears the first reply. That isn't a conversation in the ordinary sense. If someone is bleeding, struggling to breathe, or showing signs of a dangerous infection, nobody on Earth can watch the patient and guide each decision as it happens. By the time a doctor's first instruction arrives, the situation may have changed several times. Mission control can still offer knowledge, it just can't offer reflexes. And delay is only one part of the problem. NASA's work on medical care beyond Earth treats communication delay alongside mission duration, limited resupply, and severe limits on evacuation. Those problems reinforce each other. A crew may know exactly which medicine a patient needs and still have too little of it. They may identify a damaged device and have no replacement. They may stabilize someone successfully, yet have no quick way to move that person to a hospital. On Earth, medicine depends on a large world waiting behind the room. More staff can be called. Blood can arrive. A scan can be ordered. A patient can be transferred upstairs or flown somewhere better equipped. On a Mars mission, much of that hidden world has to fit inside the spacecraft before launch. The crew carries a small pharmacy, a small clinic, and a small set of trained hands. Once they leave, that inventory becomes the edge of what is possible. This is where the round trip begins to feel like exile, even though everyone plans to come home. Not dramatic exile, procedural exile, the kind written into checklists. No immediate consultation, no new shipment, no practical evacuation. A medical decision that would involve 5 departments on Earth may fall to one crewmate working from stored instructions, while another waits for a reply, still moving between planets. The return makes this harder, because the crew doesn't reach Mars and then empty the cupboards without consequence. Supplies used on the way out, or during the stay, may be supplies needed months later on the way home. A spare component consumed early can't be wished back into its locker. A medicine used today may leave less for an illness no one has met yet. Every correction spends part of the future. So Earth remains involved, but it can't remain the mission's nervous system. The crew has to diagnose, choose, and act before advice arrives. The vehicle has to support those choices with whatever was packed years earlier, and the return starts looking like a second mission already sealed inside the first, waiting for its turn. If Earth can't keep the body safe in real time, what starts failing first? You might imagine the crew's bodies as the sturdy part of the mission. Keep the air clean, the water flowing, and the vehicle intact, and healthy people should remain healthy. But outside Earth's protection, nothing dramatic has to happen for damage to begin. The clock is already running. Around Earth, the planet's magnetic field forms a kind of protective cocoon. It doesn't stop every dangerous particle, but it turns away many of them. Move beyond that shelter, and astronauts face ionizing radiation from 2 main sources. The sun throws out energetic particles, sometimes in sudden storms. Galactic cosmic rays arrive from beyond the solar system, carrying enough energy to pass through matter that would stop more familiar radiation. Ionizing radiation carries enough energy to knock electrons away from atoms. In your body, that can alter molecules, damage cells, and break strands of DNA. Cells can repair a great deal of this damage. They do it in you right now. But repair isn't perfect. As exposure continues, there are more chances for an error to remain. It's a little like keeping a house repaired during weather that never quite clears. One loose tile is manageable, so is one cracked window seal. But if the weather keeps working on the building every hour, Maintenance becomes part of living there. Your cells are doing that maintenance inside you, without noise or complaint. That makes distance biological. The body starts paying for the trip before the spacecraft reaches its destination. There may be no alarm, no sudden pain, and no visible injury. A crew can feel completely normal while tiny injuries appear inside cells and tissues. Some are repaired, some cells are removed. A few changes may persist. The danger grows through time and accumulated exposure, not only through a single cinematic event. Shielding helps. If a solar storm sends a burst of particles toward the spacecraft, dense material and a sheltered area can reduce the dose. Water, food, and other supplies can be arranged around a small refuge. That gives the crew somewhere better protected while the storm passes. Galactic cosmic rays are more awkward. Some carry so much energy that thicker walls don't provide a clean solution. A fast particle can strike an atom in the shielding and break it apart. That collision creates secondary radiation, sending new particles into the spacecraft. The wall still protects the crew, but it can also become part of the interaction. Simply adding more material doesn't settle the problem. So radiation can't be treated like a loose bolt waiting for the right tool. The environment keeps acting on the crew. Every extra day adds exposure, and every shielding choice brings trade-offs in mass, design, and which particles it can handle. Scientists can estimate doses, study damaged tissue, and test protective materials. They can't promise that one layer, one medicine, or one clever arrangement makes deep space biologically ordinary. Radiation doesn't decide the entire human frontier by itself. Health also depends on gravity, sleep, isolation, medical care, and the ordinary stresses of living inside a machine. But radiation changes what travel time means. A longer mission isn't merely more food, more fuel, and more patience. It is more time for energetic particles to pass through the place where a human body is trying, quietly and continuously, to repair itself. You know what happens when you stop using a muscle for a while? A leg held still in a cast comes out smaller and weaker. The body notices that the work has disappeared, then stops paying quite so much to maintain the equipment. Microgravity gives the whole body a version of that message. On Earth, you're always carrying yourself. Your hips support your upper body, your legs push against the floor. Even standing at the kitchen counter puts a steady load through your skeleton. You don't feel it as exercise, but your bones do. That ordinary pressure helps tell them how much structure they need to keep. Take the pressure away, and the body adjusts. It behaves a little like a building that has been told it no longer needs to support its own weight. Keeping every beam thick would cost material and energy, so the structure begins to change. Bone is living tissue. It's continually being removed and rebuilt. Under microgravity, that balance can shift toward removal, especially in the bones that usually carry weight. The hips and legs are among the places of greatest concern. Astronauts can lose roughly 1 to 2% of their bone mass for every month spent in microgravity. 1 to 2% per month may sound modest, but the mission clock keeps turning. On a trip measured in many months, a slow monthly loss can become a serious medical and practical problem. The crew still has to work, move through the spacecraft, handle equipment, and eventually face gravity again. The body is preparing for a world where weight has almost vanished, while the mission may end in a place where weight suddenly returns. Bones aren't the only parts responding. Muscles that normally hold the body upright have less work to do. Balance and coordination must adapt to floating. Ordinary movement changes because there's no floor pushing back in the familiar way. Nothing dramatic has to happen on a particular Tuesday. The crew can feel fine while useful strength and function are gradually being spent. That's why exercise in space isn't simply about staying fit. Crews use equipment that makes muscles pull and bones bear load, giving the body some of the mechanical signals it would normally get from gravity. For a few scheduled hours, resistance machines remind the skeleton that heavy work still exists, even when nothing around it feels heavy. These countermeasures help. They can slow some losses and preserve more function. But they don't make microgravity disappear. A machine can imitate parts of the load for part of the day. It can't turn the spacecraft into Earth for the remaining hours. People also respond differently, so there isn't one exact rate of decline shared by every astronaut. Recovery can differ as well. It would be wrong to treat every change as identical or automatically permanent. Still, the direction of the problem is clear. Remove ordinary load from a living body, and the body remodels itself for the environment it is now. Unfortunately, that may be the wrong body for the environment waiting at the other end. So a long voyage doesn't merely carry a crew across distance. It quietly spends down bone, strength, and physical reserve while everyone is eating breakfast, checking instruments, and going about the day. Countermeasures can make that spending slower. They haven't shown that we can erase the bill. But even a body with some reserve left depends on the systems around it. So how close can those life support systems come to replacing Earth? It's tempting to look at a nearly closed water loop and think the problem is nearly closed too. After all, if a spacecraft can keep cleaning the same water, the crew no longer needs a fresh supply from Earth, or at least not much of one. And the engineering aboard the International Space Station deserves a moment of genuine respect. Water from the cabin, from washing, and even from urine can be collected, cleaned, checked, and sent around again. NASA now reports that the station can recover roughly 98% of its water. 98%. That's an extraordinary result in a place where a broken pump can't simply wait for a plumber. Before a newer brine processor was added, the recovery rate was about 93 to 94%. The stubborn part was the concentrated waste left after urine processing. It still held useful water, but pulling that water out was difficult. The new system recovers more of it, squeezing the loop closer to closure without pretending the final residue is easy. On a chart, the improvement can look almost modest. A line moves from 93 or 94% to about 98. But imagine pouring a glass of water through a recycling machine that returns nearly all of it. Each pass leaves just a thin, wet trace behind. You barely notice. Run that same glass through again and again for months, then years, and the missing traces become barrels. That's the trouble with percentages on a long voyage. 2% sounds tiny when you hear it once. It's much less tiny when it applies to every drink, every meal, and every bit of water used by several people, day after day. The leak may be invisible at breakfast. Across a year of breakfasts, it becomes part of the ship's design. Whatever the system fails to recover has to be replaced from somewhere. On the station, replacement water can arrive from Earth, and some water is also produced through other onboard processes. Far from Earth, every replacement kilogram has to leave with you, be found along the way, or come from machinery that can keep working without rescue. The loop also needs filters, pumps, valves, sensors, chemicals, power, and people who know what to do when the water begins tasting odd on a Tuesday morning. Parts wear out, materials get used up, contaminants don't politely remain the same. A recovery percentage tells you how much water comes back under operating conditions. It doesn't tell you that the whole system can maintain itself forever. And water is only one loop. The same ship must keep managing air, waste, food, power, heat, and all the machinery connecting them. Even if each system loses only a little, those losses don't disappear. They collect into a growing list of things the crew must carry, replace, repair, or somehow make. Earth has no single water recovery percentage. It holds vast reserves and moves water through oceans, clouds, soil, rock, plants, microbes, and ice. When one pathway slows, the planet doesn't wait for a cargo vehicle carrying a replacement filter. So 98% is worth admiring. It shows that people can build a remarkably tight loop in orbit, improve it, and recover water that earlier systems left behind. But the last 2% isn't merely an untidy edge on an otherwise finished solution. Over enough time it becomes supplies, spare parts, power, maintenance, and risk. A spacecraft can become astonishingly efficient while remaining dependent on the world it left. Recycling keeps the water moving. Independence means the losses no longer lead back to Earth. Imagine a life support rack humming along beside an empty shelf. The fans are turning. The pumps are moving water. The scrubbers are pulling carbon dioxide from the air. Everything looks closed, right up until one small part wears out and the replacement isn't there. That missing part may be a valve, a seal, a sensor, or a length of tubing. Nothing dramatic. It might fit in your hand, but if the machine needs it, the whole loop now depends on something outside the loop. A closed system has to do more than recover water and clean air. It has to keep the machines doing that work alive. That means finding faults before they spread, reaching damaged components, repairing what can be repaired, and replacing what cannot. Each extra pump adds another bearing that can wear. Each sensor adds another reading that can drift. Each filter has a useful life. Reliability is partly about making better equipment. It's also about needing fewer moments when a crew member opens a cabinet and hopes the correct object is inside. NASA treats this as a central problem for long missions. The farther people travel, the less practical it becomes to rely on heavy maintenance or a steady demand for spare parts. A repair near Earth can draw on warehouses, engineers, test facilities, and launch vehicles. A repair far away has whatever crossed the distance with the crew. The International Space Station makes this easy to miss because it works so well. It's an extraordinary laboratory, but it isn't floating outside Earth's repair system. Teams on the ground watch its equipment, study failures, plan maintenance, and prepare cargo. Replacement hardware can be stored on Earth until a launch carries it upward. Experts who never enter the station still help keep its air breathable and its water moving. Earth still mails the spare parts. The idea sounds almost silly because the trip is anything but ordinary. The package rides a rocket. The delivery address is moving around Earth at thousands of miles an hour. Yet the basic arrangement would be familiar to anyone waiting for a dishwasher component. The machine can't make everything it needs, so someone elsewhere sends the missing piece. This changes what a closed loop means. You can return nearly all the water to use and still have an open chain of dependence behind the recovery unit. The loop closes chemically while remaining open mechanically. Its pumps need attention, its electronics need diagnosis, its materials age under heat, vibration, moisture, and radiation. Even careful maintenance consumes tools, time, and parts. And there's no single finish line where this problem disappears. Making one component last longer helps. Carrying duplicates helps. Designing equipment that crews can reach and repair helps. But mass and storage are limited, while failures don't politely announce which spare they'll require years in advance. Earth handles this differently because its support network is spread across an entire planet. If one workshop lacks a part, another factory can make it. If one specialist is asleep, another can answer. A spacecraft has to compress some useful fraction of that network into a very small place, without pretending every possible failure can be packed into a box. So a ship doesn't become Earth when its tanks stop running dry. It gets closer when the machinery behind those tanks can survive its own wear. And if Earth cannot send the right fix quickly enough, what keeps the loop closed then? You might imagine the delay as a very long pause on a phone call. Annoying, certainly, but manageable. You send a message, wait for the answer, and carry on. A capable team on Earth can still study the problem. They can still offer good advice. The trouble is that advice does more than move information. Sometimes it steadies a person while something is happening. Astronauts aboard the International Space Station are far from home, but conversation can still feel like a conversation. They can speak with mission teams, medical professionals, and family members with only a small delay. Someone laughs, and you hear it at roughly the right moment. A doctor can ask a follow-up while the concern is still fresh. A spouse can notice the strain in your voice and respond before you've changed the subject. That quick response is easy to overlook because it feels so ordinary, yet it is part of the support. NASA's behavioral health work draws a clear distinction between that experience and a Mars-class mission. Once messages take many minutes to cross the gap, live support becomes a chain of recordings. You explain what happened, Earth receives it later. People discuss it, record a reply, and send it back. By the time their reassurance arrives, you may have eaten, worked, slept, argued with someone, or made the decision yourself. The words can be thoughtful. The people sending them can care deeply. But late comfort is a different kind of comfort. Think of calling someone you trust after a frightening medical test. Usually their presence is part of the help. They hear where your voice catches. They ask what you meant. You correct them. They stay with you while the fear is still taking shape. Now turn that exchange into 2 recorded messages separated by long gaps. Nothing loving has been removed from the words. What's missing is the shared moment. You are being heard, but not quite being held through it. That is important for medicine too. A crew member can describe a symptom and send measurements home. Specialists on Earth may still be extremely useful, but they can't guide a fluid conversation in real time. The crew has to decide what to check next before the specialist's first reply arrives. If the answer raises another concern, the next round begins. A discussion that might take 10 minutes near Earth can stretch across hours. During those hours, the crew still has to watch, judge, and act. And then there's the crew itself. On a bad day, people don't always need a perfect answer. They need someone to react. A hesitation, a quick correction, even a badly timed joke can release pressure before it settles into the room. With delayed contact, more of that immediate work falls on the people aboard. They must notice one another more carefully because Earth cannot quietly join the conversation at the right second. Teamwork becomes partly the job of supplying the human response that hasn't arrived yet. NASA does not treat communication delay as proof that people cannot travel farther, nor does delay by itself decide where a lasting human frontier can exist. It changes the kind of support available there. Earth remains full of families, physicians, engineers, and friends who are paying attention. They simply cannot be present in the same way. The mission is still connected. It just stops feeling accompanied. Imagine 4 people inside a sealed habitat working through an ordinary problem. A piece of equipment is behaving oddly. The crew sends a careful message to mission control, then waits. By the time the reply arrives, they've already made a choice and moved on. The answer may be excellent. It may also belong to a problem that no longer exists. NASA has tested this kind of delay inside Hera, the Human Exploration Research Analog. It's a compact habitat on Earth where crews live through simulated deep space missions. They are isolated, their days are tightly planned, and their contact with mission control can be deliberately delayed. Hera isn't Mars. The crew knows that help is physically nearby, and no simulation can reproduce every danger or emotion of another planet. But an analog can still reveal what people do when a familiar support system stops keeping pace with them. Crews have described the communication delay as a meaningful operational challenge. It wasn't just an annoying pause in conversation. It changed how they planned, how patiently they worked, and how much they depended on one another. A vague request could waste an entire exchange. A missing detail might not be corrected until the useful moment had passed. So messages had to carry more of the situation the first time. The smallest habits begin to matter. A crew can bundle several questions into one message, include the readings Earth will probably ask for, and agree in advance on who decides if no reply comes in time. Ground teams can answer likely follow-ups before they are asked. None of this makes the delay disappear. It keeps the delay from turning every minor uncertainty into a second delay. You've probably had a smaller version of this in a text thread. You ask someone what to do, wait too long, make your best guess, and then receive a thoughtful reply about the choice you already made. Now imagine that thread includes engineers, doctors, and flight controllers, and the subject is the machine keeping your air breathable. That changes the role of expertise. When advice arrives inside the decision window, mission control can act like a co-pilot. People on Earth can notice trouble, ask a quick question, hear the answer, and adjust with the crew. Once the reply arrives too late, that expertise starts behaving more like a delayed library. It remains valuable. It just can't reach into the moment and help steer it. Or, to put it less politely, mission control becomes a pen pal with expertise. The crew still sends reports. Earth still studies the data and offers solutions, but both sides have to anticipate more. Ground teams must send guidance that survives changing conditions. Crews must decide which problems can wait, which need immediate local action, and what information Earth will need later. Patience helps, but patience alone isn't enough. The work itself has to be redesigned around the delay. That is what the Hera experience makes concrete. Waiting longer for the same guidance doesn't preserve the old arrangement. It creates a different arrangement, one built on precise planning and tighter teamwork aboard the habitat. The crew becomes less like the hands of mission control, and more like a small operating team, with Earth serving as a distant advisor. Near Mars, that shift is already serious enough to rehearse. So what happens when the crew isn't near Mars at all, but much farther away, around Jupiter? An asteroid can sound like the practical choice. It may contain useful metals or water-rich minerals. It has almost no gravity to climb out of, and some asteroids pass much closer to Earth than Mars ever does. Smaller rock, shorter trip, easier problem. Except the smallness is part of the problem. Imagine arriving at a tiny, irregular rock turning slowly against the stars. There's no broad surface beneath you, no horizon to help your eyes decide which way is up. You may not even be able to stand there in the ordinary sense. Push too firmly, and you could send yourself drifting away. NASA's asteroid mission studies treated that kind of flight as training for deep space operations. Crews would need to practice spacewalks, make decisions with less immediate help from Earth, and operate their vehicles as one connected system. That's a useful description of what an asteroid really offers. It isn't an easy side trip. It's a place to rehearse doing difficult work far from home. Low gravity helps with fuel. It doesn't give you air. It doesn't block radiation, hold warmth, provide pressure, or offer any of the quiet background support that Earth gives us for free. There's no atmosphere to slow an arriving spacecraft. There may be loose dust and rubble instead of solid ground. Even collecting material can become awkward when every hammer strike, drill movement, and escaping chip has somewhere else to go. So the spacecraft still carries nearly the whole burden. It must be the shelter, the power station, the air supply, the workshop, the kitchen, the communications room, and the way home. The asteroid may contain something valuable, but finding it, reaching it, extracting it, and putting it somewhere useful are separate problems. A resource inside a rock is not the same thing as a resource ready to use. Think of it as a job site with no town attached. You bring every worker, every tool, every spare part, every meal, and the building that keeps everyone alive. Then you tether the whole operation to a boulder moving through space, where even dropping a wrench becomes an orbital problem. That doesn't make asteroid missions pointless. Different asteroids have different orbits, compositions, sizes, and surfaces. Some could be scientifically valuable or useful for testing equipment without descending into a deep gravity well. Their difficulty isn't identical, and neither is their purpose. But an asteroid doesn't become a second home just because it's small or nearby. It offers very little environmental help, so almost everything that makes the mission livable must arrive with a crew. In the darkness, the destination remains what it was before they came, a tiny uneven rock with one person tied to it and no town anywhere below. Low gravity sounds like a favor. You imagine a gentle arrival, light equipment, and an astronaut hopping across the surface with hardly any effort. But once your boots touch an asteroid, the missing weight becomes its own problem. The rock doesn't hold you in place the way a planet does. It barely gives you a place to stand. Imagine trying to repair a bicycle while standing on a floating pool toy. Every push against a bolt pushes you the other way. On an asteroid, even a careful movement can start a slow drift. An astronaut reaching for a handhold may need to account for the force from each finger. Tools need restraints. Equipment needs anchors. The crew needs some reliable way to press against the surface without simply leaving it. Even routine work becomes a careful exchange of pushes and tugs. Gravity on Earth quietly organizes almost everything we do. It keeps floors beneath us, objects on tables, and liquids at the bottoms of containers. It gives our muscles a steady direction to work against. A small asteroid provides almost none of that stabilizing context. There may be a surface, but it doesn't behave much like ground. You can reach it without gaining the ordinary advantages of being on land. That's why NASA framed human asteroid operations around the work involved in making contact. Spacewalk systems had to let astronauts move and handle objects safely. Robots and crew members had to work together, because a robotic arm could provide reach or stability that a person lacked. The deep space vehicle remained central as well. It wasn't merely transport, it was the protected place where the crew could breathe, sleep, communicate, and carry out all the ordinary routines the asteroid couldn't support. And the usual dangers of deep space still came along. Low gravity doesn't block radiation. It doesn't make months inside a closed vehicle easier on the body or mind. It doesn't put Earth close enough for immediate advice when something fails. The crew still needs shielding, dependable life support, careful recycling, and enough autonomy to solve problems without waiting for someone at home to guide each step. So an asteroid offers access to solid matter without offering the comforts that usually come with land. You can touch it, you can examine it, you may be able to attach instruments or collect material, but contact isn't settlement, and a surface isn't automatically a place where normal life can take root. Almost everything that makes the operation safe and livable still has to come from somewhere else. There's a useful absurdity in all this. Humans arrive with a spacecraft built to survive deep space, then spend enormous effort making sure one gentle shove doesn't separate them from the destination. The asteroid is right there beneath a gloved hand, yet it never quite becomes a world underfoot. And this is where an asteroid can become tempting again. A dark lump of rock may contain water-bearing material, metals, or other useful substances. If crews could extract and process them, some supplies might not have to travel all the way from Earth. Water could serve several purposes. Metal could become feedstock for repairs or construction. With enough equipment, some material might even support fuel production. That is important. Every kilogram launched from Earth costs energy, money, and room aboard the spacecraft. Finding part of what you need at the destination could lighten that burden. It could extend a mission or make later missions less dependent on constant deliveries. But useful isn't the same as livable. Imagine placing a chunk of ice on one side of a scale. On the other side, place radiation protection, reliable life support, medical care, stable gravity, emergency transport, spare machinery, and enough other people to form a functioning community. The ice may be valuable. It doesn't make the other side disappear. This is how resources change the problem. They can reduce one input while leaving the larger Earth replacement system almost untouched. Water locked inside rock doesn't arrive in a glass. It must be found, mined, heated, purified, stored, and protected from loss. Each step needs power and machinery. That machinery needs maintenance. The people maintaining it still need air, food, shielding, medicine, and somewhere their bodies can remain healthy. Rescue remains a problem too. A deposit of useful material cannot shorten the distance to help. It cannot send a surgeon when someone is badly injured. It cannot replace a failed pressure vessel or create a backup crew from the people who aren't there. And the five hazards don't politely step aside because the rock contains something valuable. Distance still delays rescue and resupply. Radiation still reaches the crew. Very low gravity still affects the body and complicates ordinary movement. Isolation still presses on the mind. A hostile environment still has to be held outside every sealed room, every hour. That's why asteroid mission concepts are usually treated as tests of operations. Navigation, sampling, anchoring, resource extraction, and survival far from easy support. They can show whether equipment works and whether crews can manage a difficult destination. They do not show that a small body has quietly become an easy home. None of this makes in-space resources pointless. They may become extremely useful. A frontier supplied partly from local material could be more practical than one supplied entirely from Earth. But the material helps the mission. It doesn't teach the asteroid how to provide gravity, medicine, protection, rescue, or a social world. So if nearby rocks can offer resources without becoming homes, what happens when the destination is Jupiter itself? Jupiter can look like the next great backdrop. larger storms, more moons, a darker sky. But distance doesn't only change the view. It changes who can help you while something is going wrong. When NASA's Juno spacecraft arrived at Jupiter, its recorded one-way light time was 48 minutes and 19 seconds. A signal leaving Juno needed 48 minutes and 19 seconds just to reach Earth. You could make a cup of coffee, drink it slowly, wash the cup, and still have time left. The message would still be traveling. Now imagine a warning appears on a console. Something has overheated. A medical reading looks wrong. A navigation system is giving two answers when it should give one. You gather the information, send it home, and look at the clock. Earth cannot know about the problem for almost an hour. Once the message arrives, people there still have to understand it. They may need to compare readings, argue over the safest response, and prepare instructions. Then those instructions have to cross the same distance back. That isn't a delayed conversation in the ordinary sense. You can't describe a symptom, hear a doctor respond, clarify one detail, and adjust the plan together. Each exchange becomes a packet of history. By the time Earth receives your question, you've already spent nearly an hour living with whatever caused it. By the time its first reply reaches you, the situation may have changed twice. The same problem reaches beyond emergencies. Mission judgment usually grows through small corrections. Someone asks what you're seeing. You answer. They notice something you missed. You check again. At Jupiter distance, that familiar rhythm comes apart. The crew has to send a careful account, make the best decision available, and continue before outside advice can arrive. Troubleshooting becomes correspondence. Medical support becomes a letter written under pressure. Even a simple misunderstanding can consume hours because every clarification must travel out and back. The better the first message is, the less time everyone loses. That places a strange weight on ordinary details, which reading to include, which symptom to mention, which uncertainty to admit before pressing send. The exact delay would change as Earth, Jupiter, and a spacecraft moved through their orbits. 48 minutes and 19 seconds was Juno's one-way light time at arrival, not a permanent number for every mission, but the operational change remains. At those distances, light itself is too slow to keep Earth inside the room. A crew near Jupiter would need more than good communications equipment. They would need the authority, knowledge, and supplies to act without waiting. Procedures would have to cover situations that people on Earth might normally talk through in real time. The crew would also carry the awkward knowledge that help could be thoughtful, expert, and completely sincere, yet still arrive after the decision had been made. Earth would remain reachable, it just wouldn't be present. And once Earth is no longer present in the moment, the spacecraft has less room for anything else to go wrong. That becomes awkward near Jupiter, because almost every useful margin is shrinking at once. Start with the solar panels. Near Earth, sunlight is strong enough that we've learned to treat it as a dependable local resource. Unfold the panels, point them toward the sun, and electricity arrives. Farther out, the same sunlight spreads across more and more space. By the time it reaches Jupiter, each square meter receives only a small fraction of what it would near Earth. Juno made that difference visible. The spacecraft arrived with 3 enormous solar wings, giving it the span of a basketball court. They looked almost excessive, yet near Jupiter, all that collecting area provided only about 400 watts. That's roughly the power draw of a few bright old-fashioned light bulbs, or one modest kitchen appliance, used carefully. Of course, a spacecraft doesn't spend power the way a house does. Juno was designed to live within that narrow budget. Its instruments, heaters, computer, and radio drew from a system built around restraint. Still, the image is wonderfully odd. A machine with wings fit for a small building, gathering enough sunlight to run something you might keep on a countertop. Even sunshine has started to feel expensive. A crewed spacecraft wouldn't have to copy Juno. It might use nuclear power, different solar technology, or some combination designed for the mission. But the underlying problem stays put. Sunlight has become thin. Every watt used for heating, air circulation, computing, medicine, or radiation protection has to come from a system carried all that way and kept working for years. There's less spare capacity waiting quietly in the background. And Jupiter adds its own unpleasant contribution. Its magnetic field traps charged particles, creating radiation regions far harsher than anything around Earth. Juno survives by following a carefully chosen orbit and sheltering sensitive electronics inside a thick titanium vault. People would need protection of their own, along with food, water, spare parts, and life support equipment that could endure the long trip before Jupiter even came into view. These burdens pile onto one another. More shielding adds mass. More mass demands more propulsion. More power equipment adds more hardware to maintain. Longer missions give small failures more time to appear, and ordinary wear becomes a mission problem rather than a maintenance appointment. Meanwhile, Earth's advice arrives too late to guide every immediate response. So the change at Jupiter isn't simply that the map has become larger. The spacecraft is operating with weaker sunlight, heavier protection, older machinery, and fewer easy rescues. Even the sun offers less help. The farther the trip goes, the less support comes freely from any direction. You can imagine the control room on Earth, screens glowing, coffee going cold, a team watching every signal that comes back from Jupiter. They know the spacecraft better than almost anyone. They care about the crew. They're awake, alert, and ready to help. They're also living on the wrong clock. By the time a message reaches Earth, the moment that produced it is already gone. By the time an answer returns, the crew may have spent well over an hour living with the consequences. If an alarm sounds, you can't wait quietly for someone at home to decide what it means. You act. Then you explain what you did. That changes the relationship in a way distance alone doesn't quite capture. Earth can still provide careful analysis. It can compare years of data, spot slow patterns, and send advice for tomorrow. What it can't do is share the tempo of the people who need that advice now. Earth becomes headquarters, not partner. A partner is beside you while the problem is unfolding. Headquarters receives the report afterward. It studies the record, suggests changes, and prepares for the next time. All of that remains useful. Some of it may keep the mission alive, but it isn't the same as having another mind present in the room when a decision has to be made. Jupiter makes that difference hard to ignore because the delay arrives alongside a burden of hazards. Radiation, aging machinery, weak sunlight, and the long distance from rescue are already pressing on the mission. The crew must carry more responsibility at exactly the point when mistakes become harder to absorb. And there's a quiet social change hiding inside that practical one. A crew can still be watched without feeling accompanied. They can be studied in remarkable detail. Their voices can be recorded, their medical readings checked, their choices reviewed by people they trust. Yet the people on Earth are always responding to an earlier version of events. Support starts to feel archival, not useless, not uncaring, just late. We shouldn't pretend every crew would experience that in the same way. People differ, teams differ, and training is important. But the operating culture has already shifted. Local judgment is no longer a backup used during rare emergencies. It becomes the ordinary way the mission survives. That means the frontier can be crossed socially before anyone reaches a new world. The spacecraft may still report to Earth. Its plans may still come from Earth. But daily life has begun separating from Earth's rhythm. The crew is forming a small working society whose most important choices are made locally, because there is nowhere else they can be made in time. And if Jupiter can turn Earth into headquarters, what does Saturn do to the feeling that everyone is living through the same day? You might expect Saturn to feel like Jupiter with the volume turned up. The signal takes longer, so everyone becomes a little more patient. The crew handles more on its own. Earth waits. But there's a point where waiting stops feeling like a technical inconvenience and starts changing the shape of the day. When Cassini arrived at Saturn, mission material gave the one-way light time as about 84 minutes. That figure changed as Earth, Saturn, and the spacecraft moved, so it wasn't a permanent number. But it gives us a good Saturn-sized example. 84 minutes is 1 hour and 24 minutes for a message to arrive. A reply needs the same kind of travel time back. Imagine asking for help over breakfast. Nothing urgent. Maybe an instrument is behaving oddly, or a procedure contains a line nobody quite trusts. You describe the problem, attach the readings, and send it toward Earth. Your question is still traveling when breakfast ends. It's traveling while you clear the table, check another system, and begin the next task. By the time someone on Earth can even read it, you've been living with the problem for nearly an hour and a half. Then Earth has to think. Perhaps the answer is straightforward. Perhaps several people need to look at the data. Even if they respond quickly, their message spends another 84 minutes crossing the distance. The neatest possible exchange already takes nearly 3 hours before anyone pauses, checks a calculation, or disagrees politely in a meeting. That's long enough for ordinary human rhythm to break apart. A conversation has turns. You speak, someone notices your tone, and they answer while the reason you asked is still present in the room. At Saturn, Earth's answer belongs to an earlier moment. By the time it arrives, the crew may have changed the settings, chosen a workaround, or discovered that the suspicious reading was harmless. Earth can still offer expertise. It can study trends, revise plans, and catch mistakes that a tired crew might miss. Distance doesn't make that support useless. It changes when the support can matter. Advice becomes something folded into the next decision, not something that reliably helps with the decision already underway. And that difference reaches beyond emergencies. Meals happen, people sleep, work shifts change. Someone sends a careful explanation, then leaves the console before the response exists. The person who receives it may not be the person who asked. The two worlds are still connected, but they no longer inhabit the same social moment. A crew member sends a question while holding a warm cup at one meal. The answer arrives after the cup is washed. The work has moved on, and the next meal is being set down. Neptune is almost oddly familiar. You've seen the blue globe in books, diagrams, and photographs. It has a name you learned as a child. It belongs to the same neat row of planets as Earth. And yet, ask people to imagine sending a crew there, and the reaction changes. It no longer sounds like a difficult voyage. It sounds like sending people somewhere home can't properly follow. That response makes sense. A mission in Neptune's part of the solar system would last longer than one aimed at Saturn. Sunlight would be weaker. Solar power would demand much larger collecting areas, or the spacecraft would need another energy source. Supplies, machinery, medicine, and spare parts would have to survive years of use without any sensible expectation of quick replacement. Rescue would begin to sound socially absurd, not physically forbidden, not mathematically impossible, just so slow, expensive, and complicated that it would barely resemble what we usually mean by rescue. On Earth, rescue means somebody starts moving toward you. Near Neptune, even a successful response could spend years crossing the gap. By then, the crew would have lived with the emergency for longer than most rescue teams on Earth remain together. That's why the planet works so well in our imagination. People already respond strongly to the thought of Neptune as a place where a crew might never feel fully connected to Earth again. The blue world is recognizable, but the support around it is not. Familiar name, familiar shape, an entirely unfamiliar relationship with home. And Neptune doesn't need to be the exact line where this happens. There probably isn't one clean line. Different spacecraft would carry different power systems, supplies, medical equipment, propulsion, and tolerance for risk. A better engine could shorten the trip. A larger ship could hold more spares. Neither would turn the mission back into something Earth could casually reach. The boundary lives in the whole support chain. How long can food remain safe? Which machines can repair the other machines? How much medical care can the crew provide alone? Can the power system keep working far from strong sunlight? If a critical part fails, is another one already aboard? And if it isn't, does sending one from Earth have any practical meaning? Once those answers stop depending on help arriving in time, the crew's relationship with Earth changes. Home can still listen. It can advise, track, calculate, and care. People can send plans, voices, family news, and every bit of knowledge the connection will carry. But care is no longer the same thing as reach. That's the useful surprise inside Neptune's calm blue face. a planet can remain part of our familiar solar system while sitting beyond the ordinary social reach of home. It isn't necessarily the physical war, it's where distance starts sounding, quite reasonably, like exile. You can look at a map of the solar system and feel reassured by it. There's Saturn, there's Neptune. Earth is still on the same page. Nothing has crossed the border into interstellar space, so everything appears to remain inside the neighborhood. But familiar names on a map don't guarantee human reach. A map shows position. It doesn't show whether anyone can come for you. It doesn't show whether a replacement part can arrive while it still matters, or whether the trip home belongs to the same practical future as the problem you're facing now. The lines and labels make the solar system look connected. For a human crew, that connection can become emotionally useless long before it becomes physically meaningless. You don't need another star to feel exiled. Sometimes your own solar system is enough. Think of a remote research station during winter. It may still belong to a country with hospitals, engineers, airports, and warehouses. Everyone knows exactly where it is. Yet a storm can turn those resources into facts rather than options. Help exists. It simply can't reach the station when needed. At Saturn-class and Neptune-class distances, that temporary condition starts becoming part of the mission itself. The trip lasts so long, messages take so long to cross the gap, and rescue is so hard to imagine that routine support changes meaning. Earth may remain involved every day. It may send instructions, software, medical advice, and the voices of people you love. None of that makes a repair crew appear outside the hatch. Exile begins when return, repair, and company stop feeling like dependable parts of the same plan. They may still be possible in principle. A ship might carry enough fuel, a fault might be fixed, another mission might eventually follow. Emotional exile isn't proof of physical impossibility, and distance alone doesn't decide the outcome. Still, human beings don't live inside the phrase possible in principle. We live inside schedules, bodies, aging machines, and problems that need answers before Tuesday. When the nearest meaningful help is separated from you by months or years, rescue culture gives way to self-rescue. Shared time gives way to delayed time. Accompaniment becomes a signal from somewhere you can no longer treat as nearby. The map may say you share a neighborhood. Your body keeps a different map, measured in waiting. That puts the frontier closer than we usually imagine. It isn't marked by the edge of the sun's domain. It appears wherever home remains visible, audible, and deeply important, but no longer available in the ordinary human sense. Our probes have traveled beyond even that boundary, some carrying small records of Earth into the dark. So why can a machine make that crossing while a human mission remains an entirely different problem? Voyager 1 deserves the full measure of its achievement. In 2012, it crossed the heliopause, the boundary where the sun's outward flow of particles finally gives way to interstellar space. It did this about 122 astronomical units from the sun. That's roughly 11 billion miles, or 18 billion kilometers. Imagine that small machine crossing an invisible shoreline after 35 years of flight. No engine burned at the boundary. No flag appeared on an instrument panel. Voyager simply measured a change in the particles around it. The protective bubble blown by our sun was behind it. The space between the stars was ahead. That crossing was a triumph of careful aim, durable hardware, and patient engineering. Voyager survived radiation, deep cold, aging electronics, and decades far beyond its original tour of Jupiter and Saturn. Its radio signal reached Earth with so little power that receiving it was a little like hearing a wristwatch from across an ocean. And still, the probe kept reporting what it found. So it's natural to see Voyager and think the road is open. Build something larger, give it a faster engine, add better shielding, put people inside. But Voyager crossed alone. It didn't need air pressure, drinking water, food, warmth for human bodies, or gravity for bones and muscles. It didn't need sleep, companionship, medical care, or protection from years of accumulated radiation. It could lose instruments one by one and remain a successful mission. It could grow colder, dimmer, and quieter without suffering. A human spacecraft would have to carry a small living world, not just supplies, but working cycles, water cleaned and used again, air kept safe, waste turned from a growing problem into something manageable, food protected for years, perhaps much longer, spare parts for machines whose failure might otherwise end every life aboard. And then there are the passengers themselves. Hardware can be switched off to save power. A person can't be placed on a shelf until arrival. Every hour of the trip, the ship must remain a suitable place for a human body and mind. It has to do that while help falls farther behind and small failures have years to join one another. And none of this makes human interstellar travel impossible. Physics hasn't posted a sign saying people may not pass. The distinction is quieter and more demanding. Voyager had to preserve a functioning machine. A crewed vessel would have to preserve the conditions that make human life possible, continuously, across a distance that turns replacement, rescue, and quick repair into memories of how things once worked. Voyager's success doesn't shrink under that comparison. It becomes sharper. We sent a machine beyond the sun's protective boundary, and it kept speaking to us from the other side. But the machine carried no breathing world within it. That missing world is most of the human challenge. Imagine two spacecraft with the same outline. From a distance, they could be twins. One carries cameras, antennas, clocks, and sensors. The other carries people. That sounds like a difference in cargo, until you begin listing what the people bring with them. A probe can go silent for months, and nobody aboard becomes frightened. It doesn't need a surgeon when an appendix becomes infected. It doesn't need privacy, friendship, conflict repair, or a reason to get out of bed. If the mission lasts longer than the people who launched it, the probe doesn't have to teach its children why the mission should continue. That's why a probe is a message in a bottle. A human mission is a village in a bottle. The village needs air, water, food, and a way to recover each one after use. On Earth, we borrow those services from an enormous living system. Plants release oxygen, microbes break down waste, rivers, soil, weather, and oceans move material through cycles so large that we barely notice them. Inside a spacecraft, those cycles have to fit into pipes, tanks, gardens, filters, and careful routines. A failed pump is no longer an equipment problem. It may be a broken piece of the local environment. Then there's the body itself. Human bones and muscles expect gravity. Remove that steady pull, and the body begins adjusting to a world where strength costs more energy than it's worth. A long voyage would need some form of gravity replacement, perhaps by spinning part of the ship. Or it would need another way to prevent years of physical decline. The crew would also need protection from radiation, medical care without a nearby hospital, and the ability to handle illnesses nobody planned for. And medicine is only one kind of repair. Machines wear down, seeds fail, stored materials change, skills disappear when the only person who knows a system dies or becomes unable to work. So the village must preserve knowledge as carefully as it preserves oxygen. It needs spare parts, raw materials, tools, training, and enough flexibility to survive problems its designers never imagined. Morale isn't an optional comfort added after the engineering is finished. Neither is culture. People need trust, shared rules, room for disagreement, and some accepted way to make decisions when the original mission planners are long gone. If children are born aboard, the ship also inherits pregnancy, education, family life, consent, and the awkward fact that a trip chosen by one generation becomes the entire world of another. None of these burdens alone proves that such a voyage cannot be built. The difficulty is that they arrive together. The payload is no longer a collection of instruments. It is a continuing human world sealed inside a machine that must keep that world alive without outside help. A faster engine can shorten the crossing. It cannot by itself provide surgery, childhood, spare lungs, clean water, or a culture willing to survive the trip. The spacecraft may be larger than a probe, but the mission is not. It's tempting to answer all of this with size. Build a ship large enough, give it thicker walls, pack it with more supplies, and leave room for every machine that might matter. At some point, you imagine, the engineering becomes generous enough to absorb the danger. But enlarging a bottle doesn't teach the ecosystem inside it how to stay alive. A probe can lose an instrument and continue with a smaller mission. A human settlement can't treat failure so neatly. Its air system depends on reliable power. Its food supply depends on water, light, chemistry, and people able to maintain the equipment. Those people depend on sleep, trust, privacy, medical care, and some reason to keep doing careful work after years of repetition. Each part leans on several others, and they all have to remain healthy at the same time. That makes the problem qualitatively different from carrying extra mass. You can add another pump, but the new pump needs power, monitoring, spare parts, and someone who knows how to repair it. You can add shielding, but shielding adds weight, which changes propulsion, fuel, structure, and cost. You can add more crew for continuity, but more people increase the demand for food, water, space, and social stability. The awkward part is that redundancy multiplies the system it was meant to protect. 2 of everything sounds reassuring, until you remember that both copies live inside the same closed world. A shared chemical leak, software error, crop disease, or breakdown in trust may reach both. You haven't necessarily created independence. Sometimes you've created twice as much equipment inside the same web of dependence. Probes escape much of this because they don't need morale. They don't raise children, preserve skills across generations, or decide whether a damaged component is worth a dangerous repair. They can go quiet for months. They can be cold, lonely, and profoundly inconvenient without minding at all. Humans are less accommodating. Future engineering may reduce these pressures. Better recycling could make closure more reliable. Better materials could improve shielding. Automated manufacturing might turn raw stock into parts no launch crew could predict in advance. Medicine, agriculture, and habitat design may all improve. None of that is impossible. It simply doesn't arrive as a free gift when the ship gets bigger. Once you carry a living world, propulsion and structure are only part of the machine. The rest is a set of tightly connected biological, mechanical, and human systems that must endure together, repair themselves locally, and preserve continuity long after the original designers are gone. A megaship may give that world more room. It doesn't automatically make the world stable. So even if better engines arrive, do they solve that coupling? Or have we been scaling the wrong thing? Once you've counted all the things a crew must carry, a faster engine can sound like the master key. Cut the trip short enough, and surely everything else becomes easier. Some things do become easier. A quicker crossing means less time exposed to radiation, isolation, weightlessness, and the slow wear of a closed habitat. The crew needs fewer meals, filters run for fewer days, pumps complete fewer cycles. There are fewer opportunities for a small fault to become a serious one. Better propulsion is not a distraction from the problem. It changes the problem in useful ways. But imagine a dashboard with 5 clocks. Propulsion slows the clock-marked travel time. The others keep running. The ship still needs enough power. It still needs shielding and cooling. It still needs a way to repair itself when the right part is unavailable. The crew still needs medical care when the nearest surgeon is months away, even after a major improvement in speed. And whatever keeps the air breathable and the food growing must remain dependable every day, including the very bad ones. NASA's exploration plans treat these as connected trades. Mission designers balance mass, power, duration, crew autonomy, and risk together. Give the ship more shielding, and its mass rises. Add power, and you may need larger radiators to shed waste heat. Carry more spare equipment, and the engine has more material to accelerate. Make the engine more energetic, and the vehicle may need heavier tanks, stronger structures, or more demanding thermal control. Then the ship has to slow down. That part is easy to lose in the excitement. Arriving quickly is only useful if the vehicle can brake, enter orbit, or land without spending the entire advantage on fuel and hardware. A new propulsion system may make one leg wonderfully short while shifting the hardest engineering toward power generation, heat, propellant storage, or deceleration. None of this makes better engines trivial. A large enough improvement could open destinations that are barely practical now. It could reduce some hazards sharply. It could change which missions we're willing to attempt and how much emergency margin a crew has when something fails. It just doesn't arrive carrying a hospital, a repair shop, a stable food web, and an easy way to stop. That's how progress usually works in a tightly connected machine. Improve one part, and pressure moves elsewhere. Sometimes that movement is exactly what engineers need. It turns an impossible mission into a difficult one, or a reckless mission into a manageable one. But the next limit then becomes visible. Perhaps power, perhaps heat, perhaps human endurance, perhaps the ability to live without help from Earth. Faster propulsion moves the frontier outward. It also reveals which burden was waiting behind travel time. The wall moves, and the work continues. Imagine a ship reaching the outer planets months earlier than anyone expected. The crew sees Jupiter swelling in the window, enormous and striped, right on schedule. The engine has done its job beautifully, and now the ship has a rather awkward problem. It's still moving. A fast trip is not the same thing as a livable arrival. Unless the mission is meant to rush past its destination, all that speed has to come off again. Braking needs fuel, power, time, or some other carefully designed system. Push harder on the way out, and you may have to carry more equipment for slowing down at the other end. The quick trip has sent part of its bill ahead. Then there's power. Sunlight near Jupiter is only a small fraction of what reaches Earth. Farther out, it becomes weaker still. Instruments need electricity, pumps need electricity. Heaters, computers, radios, navigation, air circulation, and scientific equipment all need electricity. Arriving sooner doesn't make any of them less hungry. Shielding comes along too. A shorter trip can reduce some exposure, which is genuinely helpful, but it doesn't make radiation disappear. Jupiter's magnetic environment can be especially harsh, and deep space crews still need protection from solar storms and high-energy particles. Shielding adds mass. Mass affects propulsion. Propulsion affects braking. The pieces keep leaning on one another, and the crew can't arrive as passengers who've simply endured the ride. They need to remain healthy enough to work. If someone develops appendicitis, breaks a tooth, or suffers an injury that needs surgery, help may be too far away. A powerful engine doesn't remove the need for medical supplies, trained people, diagnosis, and room to treat someone while the rest of the habitat keeps running. The same is true of repair. Filters clog, seals leak, electronics fail in ways that were never polite enough to happen during testing. A distant crew needs spare parts, tools, and the ability to make decisions without waiting for Earth to study every loose bolt. Their air, water, waste, and food systems must keep closing the loop day after day, because a faster engine cannot deliver a fresh atmosphere every Tuesday. This is why the wall moves with the mission. It doesn't sit at one fixed distance, waiting for a better engine to knock it down. Improve the outbound trip, and the wall rearranges itself around arrival, survival, maintenance, and useful work. Propulsion may solve the road. It does not automatically build the town. The ship that arrives first still has to stop, shelter its crew, keep the lights on, mend what breaks, and do something worth traveling all that way to do. Speed changes the mission. It doesn't relieve the mission of having to become a small, stubborn piece of civilization. When an ambulance is coming for you, faster is better. Every minute saved can protect tissue, reduce suffering, or keep a bad injury from becoming permanent. Nobody lying beside a wrecked car asks the driver to take the scenic route. But imagine the same ambulance racing across the country and arriving at an empty field. No emergency room, no surgical team, no blood supply, no electricity. The vehicle did its part beautifully. It shortened the wait. It may have kept the patient alive long enough to arrive, yet arrival only reveals what the ambulance was carrying the patient toward. A complete emergency system is larger than its fastest vehicle. It includes people, buildings, equipment, supplies, and a long chain of ordinary work. The ambulance is one link in that chain. Improving that link helps. Sometimes it helps enormously. It just doesn't turn the link into the whole chain. You can see why speed attracts so much attention. It is easy to measure, easy to compare, and wonderfully dramatic when it improves. The rest of the chain is quieter. It looks like preparation, spare capacity, and people doing unglamorous work correctly for years. Quiet does not mean optional. That's a useful way to hold propulsion in your mind. A faster spacecraft can reduce the time a crew spends exposed to radiation, confinement, and the slow consumption of limited supplies. Shorter trips can also mean fewer opportunities for something to fail before arrival. Those are real gains. They shouldn't be softened or waved away. But speed cannot make the destination ready. It cannot guarantee that the crew can live there, repair their equipment there, or replace what slowly runs out. Those burdens still have to be met somewhere. Either the destination provides enough help, or the travelers bring more of that help with them. And the ambulance comparison has limits. A space mission is not simply a medical trip, and its risks don't all behave like an injured patient's clock. Some dangers shrink sharply when travel time falls. Others remain waiting at the far end. A few may even grow if the faster vehicle becomes harder to slow, heavier to protect, or more demanding to maintain. The analogy gives us a boundary, not a blueprint. Still, it leaves one clear image. An engine can carry people across an enormous distance with astonishing speed, then place them in the cosmic equivalent of an empty field. Getting there quickly is important, so as having somewhere survivable to arrive. So perhaps the practical limit is not the farthest place a machine can reach. Perhaps it is the farthest place where the entire chain can still close. Departure, transit, arrival, and continued life. If several of the services we quietly receive from Earth disappear along the way, where should we place that wall now? It may help to stop imagining the frontier as a line on a map. There probably isn't one clean distance where human travel suddenly changes from possible to impossible. Instead, imagine a row of switches labeled with ordinary things Earth does for us: rescue, medicine, a quick return home, live conversation, spare parts. One by one, those switches go dark. The moon turns off more than you might expect. It's close enough to see with your own eyes, yet a crew in trouble can't count on immediate rescue. Help still needs a launch vehicle, a trained team, a safe route and time. Near does not mean easy, it only means the chain is shorter. Mars removes another layer. A medical emergency cannot be separated neatly from the return trip. The return trip depends on where the planets are, what vehicle is ready, and whether that vehicle can support the crew all the way back. Messages take minutes rather than moments. Resupply takes months or years, if the launch window allows it at all. A broken pump is no longer just a maintenance problem. It may become a medical problem, a water problem, and a return problem at the same time. Then come the outer planets. Physics may still permit the trip. A machine can cross that distance, but the familiar meaning of support begins to fall apart. A reply from Earth arrives too late for ordinary conversation. Rescue may exist on paper while taking so long that nobody in immediate danger could use it. Replacement hardware cannot simply be sent when something fails. At that point, saying Earth will help starts to sound a little like offering roadside assistance to someone who has driven off the continent. That is the useful frame. The frontier is a stack of missing Earth functions. Each lost service adds something the travelers must carry, manufacture, diagnose, or decide for themselves. The ship grows heavier with equipment. The crew grows more burdened with skills. Systems need backups, and those backups need repair tools, raw materials, power, and their own backups. Eventually, too many vanished services must be rebuilt locally at once. There is no reliable equation that gives us one exact coordinate for that change. Different vehicles, crews, habitats, and acceptable risks would place it differently, but the lack of a perfect line does not leave us with no line at all. The moon shows that closeness can still withhold rescue. Mars shows how return, delay, medicine, and resupply become one coupled problem. The outer planets show how support can become socially useless long before travel becomes physically forbidden. So the human frontier is not simply where our engines stop. It is where Earth's services have disappeared in enough layers that a trip must become a self-contained world. If you tried to draw that frontier on a map, you wouldn't use a thin red line. You'd shade a widening band. Mars would sit near its inner edge. The outer planets would lie well beyond the darker side. That may sound imprecise, but it's probably the clearest view we have today. The frontier isn't a measured constant, like the speed of light. It's an inference drawn from several limits arriving together. Change the spacecraft, the crew, or the amount of risk you'll accept, and the band moves. It doesn't disappear. Mars is the first destination where the full return problem tightens around the crew. A serious illness can't be answered by sending a specialist. A damaged system can't count on a replacement arriving next week. Messages take long enough to prevent a normal conversation, and the planets keep moving while you decide what to do. Even a healthy crew lives inside a departure schedule shaped by orbital mechanics. If they need to come home at the wrong time, wanting to leave and being able to leave are two different things. Still, Mars-class missions can be designed around return. Supplies can be placed in advance. Vehicles can carry spare systems. Habitats can be built with isolation in mind. None of that makes the mission easy, and none of it guarantees survival. It does mean that Earth can remain part of the operational plan, even when Earth can't intervene quickly. Jupiter changes the character of that plan. The travel time grows. Communication becomes delayed correspondence. A medical crisis unfolds while advice is still crossing the distance. A rescue launched after the emergency would belong to another calendar entirely. Beyond Jupiter, the distinction becomes harder to soften. Earth may keep sending instructions, concern, and perhaps supplies arranged years ahead, but the crew would have to live as though immediate outside help didn't exist. That is why the present wall probably lies somewhere after the kind of return architecture we can imagine for Mars, but before an outer planet mission becomes operationally credible for a human crew. There's room inside that statement for better propulsion, better medicine, larger habitats, and much more reliable machines. A breakthrough in any one of them could shift the band outward. Moving it far, though, would require more than a faster engine. We would need to carry a convincing local substitute for nearly every service that distance removes. So no single destination gets to wear a neat sign saying, "Humanity ends here." Mars tests whether a distant mission can remain tied to Earth. Jupiter and the worlds beyond test whether that tie still counts as support. For now, the likely frontier sits somewhere between return and exile. That is a narrower frontier than most space fantasies prefer. That frontier isn't fixed, but moving it won't look like planting a flag farther from home. It will look more like repairing a ladder with a missing rung. The useful advance is the one that gives a crew back something Earth used to provide for free. Radiation protection could be that advance. A habitat that shields people without becoming impossibly heavy would return some of the safety normally supplied by our atmosphere and magnetic field. It wouldn't make deep space harmless. It would remove one service from the list of things a crew still has to borrow from Earth. Gravity replacement might move the line in another way. If a rotating habitat or some other workable system could keep bones, muscles, circulation, and vision healthy for years, then distance would stop carrying quite the same physical cost. We know simulated gravity is possible in principle. Building it into a practical spacecraft without creating a machine too large or complicated to trust is the unfinished part. Medicine has its own missing rung. Near Earth, a serious illness can become a rescue problem. Farther out, rescue may arrive months too late, or not at all. A crew would need to diagnose unfamiliar problems, perform difficult procedures, and manage recovery with the people and equipment already aboard. Autonomous medicine doesn't mean a clever box replacing every doctor. It means giving a small group enough local skill, tools, and judgment that a medical emergency doesn't automatically become a call for home. Then there's deeper closure. Air cleaned and reused, water recovered again and again, waste turned back into useful material, food produced with less dependence on stored supplies. Each improvement sounds rather ordinary beside a giant rocket. That's almost the point. Earth keeps you alive through countless quiet cycles. A distant habitat has to rebuild enough of them, then keep them working while nobody waits nearby with a spare pump. We can't rank these capabilities as though one has a proven winning score. Their value depends on the mission, the crew, the duration, and what the other systems can already do. Better shielding means less medical damage to handle. Better gravity may reduce long-term treatment needs. Better recycling reduces cargo, but it also creates machinery that must be maintained. The rungs lean on one another. So the useful test for any future breakthrough is fairly plain. Does it merely make the trip faster or more impressive, or does it replace one more thing that every crew has quietly been borrowing from Earth? Rockets determine how quickly we reach the frontier. Rebuilt Earth functions determine whether people can live beyond it, and the next line-moving capability may be the least glamorous one in the spacecraft. Which borrowed piece of Earth do we need to win back next? We began with distance. A map makes the problem look almost tidy. Pick a destination, measure the miles, choose an engine, and work out how long the trip will take. But a human frontier isn't drawn by distance alone. It appears when too many pieces of Earth have to be rebuilt inside the ship at once. Air that stays safe, water that keeps coming back clean, food that lasts without quietly losing what the body needs, protection from radiation, medical care when there's no hospital behind the next door, machines that can fail, be understood, and be repaired by the same small group of tired people who depend on them. Each problem can look manageable on its own. The trouble is that they arrive together. A damaged pump changes the water supply. Less water changes hygiene and health. Illness changes the crew's ability to repair the pump. Far from Earth, a small fault doesn't remain politely in its own category. It brings its friends. That's why there's no exact mile marker where human travel suddenly becomes impossible. The boundary moves with the strength of the little world we can carry. Right now, we know how to keep people alive in space with heavy support from Earth. We don't yet know how to make that support truly close in on itself for years, while parts age, bodies change, and help grows distant. Nor do we know how well a crew could keep fixing that world after the spare parts, easy answers, and forgiving mistakes have all been used up. Mars still sits on the difficult side of possible. Nothing we know has ruled it out. But reaching Mars and living there safely are different achievements, and neither one makes the other automatic. Beyond Mars, toward Jupiter and farther out, the trip begins to resemble exile. That doesn't mean the laws of physics forbid it. A machine can cross those distances. Several already have. A machine can go quiet, lose a component, and continue with half its original abilities. It doesn't need clean water. It doesn't grieve. It doesn't have bones, blood, or a crewmate who wakes at 3 a.m. with a pain nobody can diagnose. People need more than a working trajectory. They need a living place, and they need it to remain living on an ordinary bad day when someone is exhausted, something leaks, and the repair doesn't work the first time. Perhaps the capability that moves this frontier most will be a nearly closed life support system. Perhaps it will be better radiation protection, artificial gravity, or machines that can repair and reproduce essential parts. We don't know which missing piece will prove decisive, because the first long trips will test all of them together. So the limit of human travel is narrower than the opening map suggested, and much more human. It isn't simply where the fuel runs out. It's where the ship can still move, but the small piece of Earth inside it can no longer be kept alive with confidence. Our spacecraft may travel very far before we learn how to bring a human world that far with them. For now, that quiet difference is the frontier.